So, note 6.5, using logs and exponents to solve equations. So, first of all, you can see we've got the natural log of x plus the natural log of the expression x minus 8, and that's going to equal 2 times the natural log of 3. So, first thing we want to do is go ahead and apply our log laws. So, can someone tell me what this adding of the logs is going to tell us to do? Multiply, absolutely. So we can say this would be the natural log, and this would be x times x, or x squared, and then the x times the subtracting 8 would give us a negative 8x. And then someone else tell us what this 2 going to tell us to do. Say it a little bit louder. Yes, it's going to be the exponent. So we're squaring that 3, which means we have the natural log of not 3, but 3 squared, which is 9. Yeah. Now from here, remember we had the law that said if we have the natural log of m, and that equals the natural log of n, well, the only way that these two can be equal to each other is if, of course, m equals n. So over here, we have the natural log of this expression. That equals 9. So we can basically just solve on the inside of this, okay? Which would mean that we would have x squared minus 8x equals 9. X squared minus 8x minus 9 would then be equal to 0. That's a fun one because it can easily factor. The 9 is negative, so we know one of these is going to be negative. The other one's going to have to be positive. And 9 times 1 will give us 9. And negative 9 plus 1 would give us the negative 8. So let's make this a negative 9 and plus 1, which gives us 2 solutions. The first of which would be x equals 9, and the second one would be x equals negative 1. Now, one thing we didn't do, and that was to check our domain. So if you'll look up above, we do have the natural log of x here. So if we were looking at the domain, that one's quite simple. X just has to be greater than 0, which causes us to say, oops, this x equals negative 1 is not going to be one of our solutions. Okay? But let's not stop there, because there's another expression, this x minus 8, that also has to be greater than 0. Adding 8 to both sides, x has to be greater than 8. Take a check over here and look, and 9 is definitely greater than 8, so it is in our domain. So that is our solution. Only one solution out of that one. Okay? All good? All right, next one. We have used this before, but in our previous ones, we were always looking to get the common bases, and then we just set our exponents equal to each other. And we're not going to be able to get any common bases on this one. So let's pull out that little trick of, if I want to get exponents out to solve those, I'm going to take the natural log of both sides. So this will be the natural log of 5x minus 2 equals the natural log of 3x. And I'm sure if you were doing this problem, if I were doing this problem, I would not write this step at all, because why are we doing this? We're doing this because when we take the natural log and we take the natural log of something with an exponent, that exponent can be written as the coefficient. Okay? So just for clarity, I wrote that. I don't think any of us would start there. We would say, okay, this is going to give us the x minus 2. Put that in parentheses because that's multiplied by the natural log of 5. And that's going to equal, on the other side, x times the natural log of 3. Well, I need to get these x's by themselves, so we're actually going to have to go ahead and distribute. So this will give us x times the natural log of 5 minus 2 times the natural log of 5 equals x times the natural log of 3. So I think I'm going to probably, let's move our x's over here to this side, and I think I'll move this guy over to the other side. So I'll get my x's on the left-hand side by subtracting this x times the natural log of 3. And while I'm at it, let's add this to natural log of 5 to both sides. And of course, these give us 0. And we end up with, I'm going to go ahead and factor the x out while we're at it. I'm going to save a step here. This would be x times the natural log of 5 minus the natural log of 3, and that's going to equal, on this side, 2 times the natural log of 5. Which means x would equal 2 times the natural log of 5 divided by the natural log of 5 minus the natural log of 3. Whatever that is, there's a little bit of simplifying we could do with that one, or just leave it like that. Okay, let's take a look at the next one. And this one, same approach we did before. Okay? And that is take the natural log of both sides to get this exponent down so we can do some solving. So, like I mentioned before, I won't write that I'm taking the natural log of both sides and then do the exponent rule. I'm just going to use that exponent rule, write this 2x minus 1 as the coefficient, and this will be times the natural log of 3 equals the natural log of 7. Okay. This time, I'm not going to distribute. Let's just, since we don't have any x's on this side, let's just go ahead and divide both sides by the natural log of 3. That will give us a 2x minus 1 equals the natural log of 7 divided by the natural log of 3. Now, I want to make sure we understand the simplifying here. I'm going to go back to this guy, and we know that this 2 can be written as the exponent, so the numerator can be written as the natural log of 25. And since we're subtracting logs, we can write this as the natural log of 5 divided by 3. And why did I go back and do that? Because a lot of times people want to try and simplify this one. And unfortunately, you know, it's not going to work backwards into a subtraction problem. And then also, the natural log of 7 divided by the natural log of 3 is not the natural log of 7/3. And then also, believe it or not, we've seen this one before, the natural log of 7 divided by the natural log of 3. Well, the natural log divided by the natural log gives us 7/3. And no. Okay, neither one of these are ways that natural logs simplify. Okay? It's just going to be whatever the calculator puts out with the natural log of 7, divide that by the natural log of 3. We good with that? Don't try and apply rules that don't apply. Okay? But you can see our algebra steps would be add 1 to both sides and then divide by 2. So it gets a little bit cumbersome to write, but this will be the natural log of 7 divided by the natural log of 3. We added 1 to both sides, and then we divided by 2. So something like that. And that would be acceptable. Okay. All right, let's take a look at the next one. Not wanting to take the natural log of both sides here because this whole thing would be inside that natural log. But hopefully you can see there's some simplifying we can do here. Since this is 4 is 2 squared, we can write 4 to the x as 2 to the 2x minus 2x, and then we'll put minus 12, and that equals 0. Yeah. Now, maybe another way would be a way of solving this one. But I do see something that we've done before. Let's think of it this way. Let's say that this is 2 to the x squared minus, I'll even put a negative 1 in front of this, 2 to the x minus 12 equals 0. Can you see that this actually kind of acts like a quadratic? We've got something squared plus something to the first power equals this. Doesn't that kind of mirror something that might look like, say, x squared minus 1x minus 12 equals 0? Yeah? So this might be a little shortcut that we can use, which means that we could write this as 2 to the x, because 2 to the x times 2 to the x will give us 2 to the x squared. And we see that we have a 12 here that's a negative, so one's going to be negative, one's going to be positive. And we know that 3 times 4 will give us 12, and they are just 1 apart. And since the negative is in the middle, we'd have to make the 4 the negative and the lower number 3 the positive. Which means we can solve this by saying 2 to the x minus 4 equals 0, or 2 to the x equals 4. And on the other side, 2 to the x equals 0, or negative 3. Let's solve this one. I think most of you can just look at that and know what that's got to be. So obviously 2 squared is 4, so x equals 2. But we do have a little dilemma here. Can we ever get this to be a negative number? No, not going to happen. There's no way we can get a negative out of that. So in the end here, we have only one solution, and that is this guy right here, x equals 2. Love this stuff. All right, let's take a look at number 1 here and see what we want to do here. Well, what I'm going to suggest we do is use that same technique we did here on this one. Let's rewrite this 9 to the x as 3 to the x squared. 9 is 3 squared, and when we do a power to a power, we're multiplying, so it doesn't matter if we do 2 times x or x times 2. And then this would be minus 5 times the 3 to the x, and while we're at it, let's just add this 6 to both sides. The factoring just jumps out at us because we see that we have a positive 6 and a negative in the middle, so both of these are going to be negative. And of course 3 times 2 gives us 6. meaning we have one solution here when 3x minus 3 equals 0, or 3 to the x equals 3. Pretty obvious. The only way that's going to be equal is if x equals 1. There's one solution. Let's do the other one. This would be when 3x minus 2 equals 0, or 3 to the x equals 2. This time we will have to do our log law, our exponent rule here, which would mean x times the natural log of 3 equals the natural log of 2. Dividing both sides by the natural log of 3, we'll have the natural log of 2 divided by the natural log of 3. Like we pointed out up above, no simplifying, that is it. So this one actually has two solutions. When x equals 1, and when x equals the natural log of 2 divided by the natural log of 3. Alright, let's take a look at number 2. And we'll get a little bit of involvement here. Carter, when we take the natural log of both sides, what will we have on the left side?
X plus 4, natural log of 2.
X plus 4, that quantity times the natural log of 2. Good job. And then, Jack, what will we have on the right-hand side?
Natural log of 7x.
And then, yeah, we'll just put, and if you mind if I put that in front of it, so it's x times that. Very good. All right, I think we need to do some distributing on this one, because this one was similar to example number 2 up above, where we have x's on both sides, so we want to distribute and then move our x's. Okay. So this will give us a x times the natural log of 2 plus 4 times the natural log of 2 equals x times the natural log of 7. Let's go ahead and why don't we move our x's on this side, since this is positive. We'll just leave this guy right there. So this will be 4 natural log of 2 equals x times the natural log of 7 minus this guy here, x times the natural log of 2. We can factor out the x's on this side, and this will be 4 times the natural log of 2 equals x times the quantity of the natural log of 7 minus the natural log of 2. Dividing both sides by this natural log of 7 minus the natural log of 2, and moving it around, we'll have x equals 4 times the natural log of 2 divided by the natural log of 7 minus the natural log of 2. And yes, we could take this 4 over here to the 2 and take 4 or 2 to the 4th power, and we could simplify in here if we wanted to. I'm just going to move on to the next one. All right, and then Connor, I think we need to do the natural log of both sides here. What will we get on the left-hand side if we take the natural log of that?
Natural log of 2 times 3x plus 2.
Very good. Natural log of 2 times the quantity of 3x plus 2. And of course we'll have the natural log of 3 over here. This one, similar to example 3 up above. No need to distribute this. Let's get this x by itself by dividing both sides by the natural log of 2. The result will be 3x plus 2 equals the natural log of 3 divided by the natural log of 2. Couple quick algebra steps of subtracting 2 and dividing by 3. We can probably jump to x equals, remember the natural log of 3 divided by natural log of 2 doesn't simplify, and we're subtracting 2 from that before we divide by 3. All right. Let's take a look at number 4. Okay. And first thing, it has this addition here. And Charlie, what's this addition going to tell us to do? Multiply. So this will be the natural log of the quantity of x minus 1 times the quantity of x plus 2. And then, Sam, what's this 2 going to tell us to do?
To the right side.
This 2 right here. Be more specific. That 2 in front of the natural log of the quantity of x minus 3. What's that going to tell us to do? No. Yes, absolutely. This is the natural log of the quantity of x minus 3, and that's going to be squared. Now, I see that we've got the natural log of something equals the natural log of something else. So we're just going to make both of those things equal to each other and forget about the natural logs. Turn it into an Algebra 1 problem, which you can see on this side. We can FOIL this through and get x squared plus 2x minus x would be plus x, and then minus 2 equals, and square this guy. We know how to do that. We square it, and then the negative 3x gets doubled to make us a negative 6x. And then negative 3 times negative 3 will give us a positive 9. Now, when we subtract the x squareds from both sides, we get rid of those. And while we're at it, let's go ahead and add 6x so we get a positive coefficient with our x's. And since our x is moving this way, let's move the numbers on the other side. Sure looks like we'll end up with 7x equals 11. Or x equals 11 sevenths. Now, before we jump to the next page and circle this, remember how we ended up with the solution over here when we checked our domain. Okay? And probably is a better idea to check your domain at the beginning, but hey, at least we're going to do it before we say this is our answer. Okay. Now, there's actually 3 different spots here where we need to check our domain. This one, x minus 1 has to be greater than 0. Add 1 to both sides. So this is telling us that x has to be greater than 1. 11 sevenths is greater than 1. Checks out. But let's check this guy. Okay. This is x minus 2 has to be greater than 0, or x has to be greater than, subtract 2 from both sides, a negative 2. Awesome. We're 2 for 2. All we have to do is make sure we're good on this one. And this one, x minus 3 has to be greater than 0, or x has to be greater than, oops, we're not greater than 3, are we? So this will work nice on this side. We'd get positive numbers inside there. But over here, we'd end up with a negative number that is not going to work. Okay? And remember, hopefully you remember this usually occurs when we do that squaring masks negatives. Okay? So the squaring would work this back to a positive, but it's not going to work in our domain. So this one actually ends up being no solution. All right, so those were some fun things of solving. Now let's use those logs to do some real-life problems. Okay? As some of you have studied in physics, the Newton's law of cooling. Yes, this guy from way back when, before calculators came up with this equation. Is that crazy? But it looks like this. Now, make sure you understand the parts of this. Okay. So, in this one, T is the constant temperature of the surrounding. Okay. So that's the room temperature. If you bring something hot in here, it's going to cool off. If you bring something really, really cold in here, it's going to warm up. It's going to try and get to whatever the room temperature is. Okay? So that's what that is. Okay? And then U sub 0, sometimes you'll see it written as T sub 0. I don't mind if you use that either. But that is the initial temperature of the object. If we bring some ice in here, what's the temperature of the ice? If we bring a big hot cup of coffee in here, it's the temperature of that coffee. Okay? And then there is K, which is some constant, and it also makes a note here that it's negative because it's cooling. Okay, you're cooling something off. Of course, if you put something in an oven and you're warming it up, then it's going to be a positive value, so it's going to be going in the other direction. Okay? So the rest of this is, oh my goodness, can we say it? Absolutely. Just plug and chug, right? Yes, you got it. Here we go. So we've got an object heated to 100 degrees Celsius, and it's allowed to cool in a room with a constant temperature of 30 degrees. So right from the start, we know that the 100 is this U sub 0. U sub 0 equals 100 degrees. And then this 30 is the temperature of that surrounding. That is our T equals 30. Okay. And then it says in the first part of this, it says the temperature of the object is 80 degrees after 5 minutes. When will the temperature be 50 degrees? So, one thing that I found works well for students on these is to do a little T-table with your information. Okay? The first one being, or the first column, is the time, and I didn't point that out up here, but T is how long it's been in whatever space that is. Okay? So we've got T, and then this will be that final U of T, that final temperature of that, or whatever temperature is associated with that. Okay? So the first one we know, when time is 0, when it's brought in there at the start, we are at 100 degrees. It gives us a second point here, and that is after 5 minutes, we're at 80 degrees. And then it's asking us, when will the temperature be 50? So this is what we're solving. Like I said, make a T-table. It just helps you organize your thoughts and organize your way of attacking this. Okay? So, from the very start, we can actually substitute in some of this information. So, U of T will equal, remember this is T, plus the surrounding, the initial temperature minus the surrounding temperature. And then this will be times e to the kt, or let's just put this as 30 plus 70 times e to the kt. Okay. So we got that right from the start. And then we can start substituting in some values here and see if we can solve this thing. Okay. So let's go ahead and put in time of T and the temperature of 80. That's going to allow us to solve for K. Okay? So this will be 80 degrees equals 30 plus 70 times E, and then it'll be a 5 times K. The T is 5 times K. Let's subtract 30 from both sides. And while I'm at it, I'm going to divide by 70. So 80 minus 30 is 50. Divided by 70 gives us e to the 5k. And you can see why this is in this natural log portion, because in order to get that k solved, we're going to take the natural log of both sides. In other words, 5k will equal the natural log of 50 divided by 70, which of course could simplify to 5/7. So k equals the natural log of 5/7, all of this divided by 5, or multiplied by 1/5 if you want to write it that way. Okay. Now that we know what our k value is, we can substitute in the 50 for the u of t and work backwards to find the t, or the time when that occurred. Okay. So this will be 50 equals 30 plus 70 e, and since I ran out of room, I'm just going to put this in parentheses, and that's just whatever this k number right there is. And then that, of course, is multiplied by the t that we're solving for. So, to get this by itself, we'll subtract the 30 from both sides. That'll give us 20, and then divide by 70. So, in other words, 20 divided by 70 will equal this e times, again, this is that k. I'm just not writing it in there because I don't have much room at all. And just like we did over here, in order to solve for t this time, we'll do the same thing. We'll take the natural log of both sides, which means the natural log of 20 divided by 70 would simplify to 2/7 equals this, again, this k value times t. So dividing both sides by this k would leave us with t equals the natural log of 2/7 divided by all of this again, the natural log of 5/7 divided by all of that divided by 5. Fortunately, my calculator was working a while ago, and when I put it in, I got 18.616 minutes. A little less than 19 minutes to drop from 100 degrees to 50 degrees. And the next one says, based upon this same scenario, what will the temperature be after 10 minutes, after 20 minutes? So each one of these are giving us a t value, and we're just solving for u of t. In other words, u of 10 and u of 20, which would be 30 plus 70 e, and I'll put that natural log of 5/7 divided by 5, that's our k value, times, in this case, 10. And it sure looks like I'd probably put this in my y1 so that I can solve both of these relatively quickly by doing the exact same thing, except raising it to this times 20 as the exponent. And if you want to check your work, your ability to use your calculator, you should get 65.714 degrees after 10 minutes, but only down to 48 degrees 0.221 after 20 minutes. Now, it's asking here, is the cooling rate constant? Okay, and that would imply, if it were constant, that our temperature would be just dropping down in a linear manner. Well, let's kind of check this and see what we had. Okay, so if you look at what we just calculated here, We know when we were at, well, we also know this one too. At t equaled 5, we were at 80 degrees. At t equaled 10, we dropped to 65.714 degrees. And then when t was 20, we're down at 48.212. Yeah. So let's just compare here. You can see that this drop from 80 down to 65.714, that's a drop of 14.286 in 5 minutes. Okay, so if I divide that by 5, it gives us a rate of negative 2.857 degrees per minute. Well, let's compare this, because if it's constant, then both of these should be the same rate. Okay. So we'll take the 65.714, subtract the 48.221. That gives us a drop of 17.493, and this is not over 5 minutes, but from 10 to 20, that's 10 minutes, which I think we can all do without a calculator here. Dividing this would drop us at a 1.7493 degrees per minute. So no, it's not dropping at the same rate. Okay? As a matter of fact, the hotter it is, the faster the rate of cooling is. As it starts to cool down, it gets slower in its rate of change. So it's going to be dropping more like this as it approaches that, rather than a linear. Okay? All right, let's take a look at another application of logs. Okay? Exponential type functions. The Newton's law of cooling, of course, resulted in that exponential decay with that temperature loss rather than a constant rate. Well, let's take a look at a logistic model. Logistic model is a more realistic growth curve based upon the idea of a natural maximum. Okay? So, for example, if I have a bacteria that I put in a petri dish, we know that its growth ends up going like this. Okay, did you guys ever do that? And made that? Okay, and did not the bacteria grow? And what did you guys do? Did you check on like the drinking fountains, and did you do something like that? Swab the drinking fountain and do that? Something in the bathroom? Okay, so your bacteria grew, didn't it? And it grew exponentially. But wait a second here. Is our room filled with bacteria right now? Is there no room for air because there's so much bacteria in here? I mean, that theoretically what should have happened, right? If that bacteria is growing exponentially, it should have approached in almost an infinite amount of bacteria, and how long ago that was. Okay, but we know that that doesn't occur. Okay, in real life, what happens is we reach this point where, oops, things don't increase as much. Okay? It ends up looking like this. The best example I can give for you on this is if we started a rumor here. Okay? Rumor that Mr. Dunn actually won the Mega Millions lottery. And he decided, since he had the best CCP college algebra class he's ever had, that he was going to give each one of his students $1 million. Okay? What do you think would happen if I announce that to you guys right now? You think you guys would just kind of keep it to yourself? No. Okay? You'd probably tell a few people, wouldn't you? Okay? As soon as you got out of here, I'd be saying, first of all, put your phones away. You can't tell mom. Okay? You got to keep it to yourself. Okay? So since there's no phones allowed in here, it would have to stay in this building, right? No one outside of this building would know about it. But would you, probably first person you see, hey, guess what? I'm a millionaire. Mr. Dunn's going to give me $1 million. He won $500 million, and he's going to give me $1 million. Everybody in our class is getting $1 million. Okay? Now think about how that's going to happen. Next person you're going to see, you're going to tell them, right? And the next person you're going to see, you're going to tell them. So, but wait a second here. How long is it going to take before you run into somebody and, well, you weren't the only one telling. Wasn't Jack telling somebody? Nick was telling somebody? Rachel was telling somebody? All of a sudden, maybe about an hour from now, you're going to run into somebody and say, hey, did you hear? And they said, oh, I already heard. And then you run into somebody else, oh, I already heard. Okay? So you can see at the beginning, you're able to tell a lot of people, but then you start reaching a point where you're trying to tell people, and they're saying, I already know, I already know, I already know. Okay? And then, at some point, we finally get that one kid who's got his hair covering up his earbuds and hasn't heard a single thing other than all day long in his ears, right? Okay? And all of a sudden, one pops out and, hey, did you hear what? Well, I didn't hear anything. Okay? Hey, everybody in Dunn's class is getting $1 million. Okay? And we finally reach that point where everybody in the school hears it. Now, can we ever go over that number? No. Okay? So that is the natural maximum that everything that has exponential growth does. You reach a point in that petri dish where the bacteria doesn't have enough food to keep going. Okay? It's going to max out, and now there can be no more on that. We do the same thing in a forest. There's only so many deer that can fit in that forest before they reach a point where there's not enough food, there's not enough space. Fish in a pond. Does any of you guys have a pond? No ponds? Okay. So if you put fish in that pond, there's going to reach a point where, that fish, there's no longer enough food, so they're going to not keep increasing exponentially. They're going to reach that maximum point. Okay? So, believe it or not, all of those examples that I gave you match this formula right here. Whether it's rumors, whether it's bacteria, fish in a pond, deer in a forest, this is the model for logistic growth. Okay? So, in this, there is C, and C is that what we call the carrying capacity. It's that maximum level. In my graph up here, okay, this value right here is where C is. That's that maximum that we reach. Okay? And we call this point here, where using some fancy words from pre-calc, where we turn from concave up to concave down. That's called the inflection point. Okay, where the rate is increasing, and then the rate of growth starts decreasing. Okay? It's still a positive increase of number of people, but the rate is what changes at that point. Okay? So let's do a quick little example here using fruit flies. Fruit flies are placed in a bottle, closed up with a banana in there. So they've got plenty of time to eat, and they've got that banana to just have fun with it. Okay? And here's our equation. Now the other thing that's in here is this value of t, and that of course is the time, in this case in days, that this is growing. Okay? What they've already done is they've already studied this, and this constant in here has already been solved for us. Okay? So that constant actually tells us something about this. Okay? So first of all, let's analyze this, it's asking for that carrying capacity, that maximum level. That one's just it's an easy quick read. That's always the numerator here when it's written like this. So our carrying capacity is 230, which is telling us that there are 230 would be the maximum number of flies in this thing. Okay. And then next, it's asking for that growth rate. Okay. This value right here, at least the absolute value of that, is our growth rate. Okay? So our growth rate is actually, and that's a b up here in the equation, it's the absolute value of that b, or 0.37, which of course we can write it as 37%. Okay? It's growing at a rate of 37%. Okay. Now it says, what is the initial population of the fruit flies? This is find t of when t equals 0. Okay? Or find p when t equals 0. So we're just going to take a look at this. This is 230, and then 1 plus 56.5 e to the negative 37 times 0. Wait a second. Negative 37 times 0 is 0. E to the 0 is going to give us 1. So this ends up being 230 divided by 1 plus 56.5, or 230 divided by 57.5, and that actually gives us 4 measly little flies to start out with. The next one says, what's the population after 5 days? So that's t equals 5. So we'll just substitute in the same equation. And I think this is when I would get my calculator out and put in this probably in the y1 and evaluate this. When we put that in our calculator, this will tell us that we have 23 flies after 5 days. Love this stuff. Looking good. All right, next one. How long does it take for the population to reach 200 flies? Okay, so 200 flies would mean we're looking for a t. We're not substituting in 200 for the t. We're setting this equal to 200. Negative 37 times t. Forgot my e in there. Okay. Now, if I were using my calculator, I could just find the intersection of that. But let's just go ahead and do the algebra to solve this. What I'm going to do is multiply both sides by this to get that out of the denominator. And while I'm at it, I can just go ahead and divide both sides by 200 so that we have 1 plus 56.5e to the negative 37t equals 230 divided by 200. Let's subtract 1 from both sides and divide by the 56.5. E to the negative 37t equals this. I can drop those zeros off there too, can't I? 23 twentieths minus 1 divided by 56.5. And now we'll go ahead and take the natural log of both sides to get this negative 37t down here. And I'm taking, oh, wait a second here. Let's simplify this. If I have 23 twentieths and I subtract 1, I'll be left with 3 twentieths. All of that is divided by 56.5, and I'm taking the natural log of that mess. And I sure wish I would have just taken the time to put that in my calculator and solved it, but anyway. We've gone this far, so let's just go ahead and finish this off. This would be t equals this thing, the natural log of 3/20 divided by 56.5, and then all of that gets divided by -37. Fortunately, I put that in the calculator earlier and got 16.030 days. Okay. 5 days to get to 23 flies, and 16 days to get to 200 flies. Now the next one says, what is the inflection point? Okay. So the inflection point is really, really cool, because if I'm looking at this graph, and in this particular case, our carrying capacity was 230, the inflection point always is going to occur when we reach half of that. In other words, when C equals 15 is when that will occur. Okay? That at least is the number of fruit flies, but it's asking for the inflection point. So we need both an X and a Y. We know that this value is going to be 115 flies. We need to work backwards to find that time in days of when that would occur. So it's similar to what we did right here. We're going to put the 115 here, 230 divided by the 1 plus 56.5 e to the -37t. And this time, I probably learned my lesson from all of this over here. I think I just put that in the calculator, graph this beautiful little exponential growth, and then find that intersection, and it's going to give us the t value or x value down here, which ends up actually being, after 10.903 days, we reach our inflection point. So 10 days will be halfway to our max. All right. What do you think? Love this stuff.